Okay, so we're going to talk about 3.7 lecture notes, conservation of momentum. And I'll kind of discuss the blanks here as well as the first example. So system, what is a system? A system is when all the objects, it's basically all the objects involved in the problem. So like say, for example, I have a car. And it's headed towards another car that stopped. So that whole thing can be considered a system. Usually only contains two objects. Internal forces are forces that the objects exert on each other. External is from the outside. So external could be like friction or like air resistance. Those are examples of external forces. And I'll tell you that that's happened, but usually we'll ignore it to make the problem simpler. So laws of conservation. So in an isolated system, so basically you have just focus on one system, the total momentum remains constant. So the initial momentum of your system equals the final momentum of your system. You want to definitely identify the forces that are going on. Is system isolated? Let's not worry so much about that. I'll basically will always give you an isolated system, so don't worry so much about that. Set the total initial system of that system equal to the final momentum. Obviously, we want to do that. So this right here, number 4, is when you're actually conserving the momentum. So let's look at an example over here. 2 billiard balls are colliding on a table. In order to play a law of conservation momentum, what should the system be? One ball or both? Well, obviously, we want to look at both. I think that's pretty clear because one's colliding with the other. External forces, weight, and normal force. Yeah, okay. If the table's horizontal, these kind of cancel out, so it's not sloped, so you're fine there. If we're one ball, then the force of the second ball hitting it would not cancel. I'm not sure what they mean by that. If it were one ball, I'm a little confused by that. Let's just kind of ignore that. It just seems kind of weird to me. Because obviously I want you working with both billiard balls. So yeah, anyway, let's do some problems. So any questions about this? And by the way, the answer keys are all up in Schoology, and I am recording this too. So again, a system is you're looking at all the objects involved in the collision. The internal forces are what's going on between those two objects. External is anything from the outside, which we're really not going to consider to make the problem simpler. We try to keep this isolated, meaning we're not having any other systems or anything else playing a role. And really what you're doing is just setting the initial momentum equal to the final momentum. That's really what we're doing over and over again. So it should be pretty straightforward problems. So let me clear. Let's actually look at these two, and then we'll look at the answer key after that. Once I finish these two, I should maybe need about 10 minutes or so. Then I'm gonna have you guys try some problems over here. Maybe we'll do like, I'll have you guys do like 5, 6, 7, 8 perhaps in the breakout rooms. Those look like good ones. And then when we come back from lunch, then we'll do 9, 10, 11, 12. And maybe I'll have a discussion about these conceptual ones. And then we're also going to look at 3.8 today as well. These are a little bit more intense. We'll have to cherry pick the ones we'll do, but we'll definitely talk about that as well. Anyway, but again, these should be pretty straightforward. Again, just conserving momentum. So again, we're recording, I'm sharing the screen. So a hockey puck of mass 0.17 kilograms and a velocity of 5 meters per second is caught by a 0.15 kilogram mitten laying on the ice. Was a combined velocity after the puck is in the mitten. Okay, so what you want to do is kind of draw a picture first. I would strongly suggest you kind of do that. So here's the hockey puck. It's going that way. And then, of course, here's the goaltender. And that's the net. Okay, it looks like a net. I don't know if that makes sense. And of course, he has, I'm not sure we call it a mitt. I would call it a glove, actually. But anyway. So it's going towards the mitten, right? And remember, this is a mass of 0.1. So in kilograms, your initial velocity is 5 meters per second, right? Then, so this is the before. The after, now the puck is in the mitten, right? So it's in there. So it's almost like it's a combined mass. And if you think about it, I mean, I've never played hockey, but if something's coming really fast, like baseball, I played softball, but if it's coming really fast, once I catch it, my hand's gonna move back a little bit, right? Because you're absorbing some of the momentum that's coming at you. So we will need to figure out the velocity, the final velocity we don't know. So the way you're gonna set this up, so it's a little bit weird. I'm gonna do it right above here, cleaning up some space. We'll do M1 times V1 initial plus M2 times V2 initial equals, now you're combining the masses because it's a combined velocity after puck is in the mitten. So that's how you know it's combined. It's combined mass. So I'm actually gonna do this, M1 plus M2, and I'm just gonna call it VF because it's now combined. So that's how you have to look at it. Now, if you think about it, obviously the mass is 0.17 for the puck, velocity at 5. The mass of the mitten is 0.5. However, that initial velocity is 0 because it's not. It's kind of just waiting there, waiting to catch the puck, right? And then you have 0.17 plus 0.5 times VF. Work all out. You should get 0.85 on this side, I think, and 0.67 on this side. Final velocity, and it's going to go back. It's going to, so right now we're considering this a positive direction. So the mitt's going to continue moving in that direction once it catches the puck. So it moves back about 1.27 meters per second because we're conserving the momentum. We're not assuming there's any thermal energy or friction or anything, or air resistance or weight of the puck. We're not worried about any of that stuff. And so if I take a look at the solution key, yeah, 1.27 right there. That's exactly what they did. And you could, if you wanted to, for the right side, for the final momentum, they did 0.17V and 0.5V. They're assuming the same velocity. I like combining them. I think it's just a little cleaner if you do it that way. And you just hold it's combined, so you know you can add the velocities. Sorry, add the masses. Any questions? Go ahead.
Where did you find this equation? Is this?
Oh, that's so it's right here. P0 equals PF.
Oh.
So P0, remember P0 is going to be the initial momentum. And excuse me. So let me actually backtrack just a tad. All this right here is P0. All this is PF. And remember, P is momentum. But remember our system, that's why we had that discussion about system. Our system involved two objects, right? So you have the mass times velocity of one and mass times velocity of the other. And you combine it, or not combine, but you add them to get the initial momentum. So you look at the puck, has mass, has a velocity. You look at the mitt, has a mass, no velocity. So basically it's just an extension of momentum, right? And then afterwards, my final, the puck is in the mitt, so that counts as one object now, if you want to think of that as combined. And that has a combined mass of 0.67, and then there's a little bit of velocity with that. So it's just a mass times velocity, but you have multiple objects. You have to do the individual MVs, at least for before, because they're not combined yet. Hopefully that makes sense for that one. All right, let me clear the drawings. Again, I am recording this. I'll probably need a little space, so I'll probably position it this way. A 5-kilogram baseball pitching machine is placed on some frictionless ice, okay? It shoots 0.15 kilogram baseball horizontally at 35 meters per second. How fast is the pitch machine moving after it shoots the ball? Okay. So it's a little tricky. Let's see if I can figure this one out. So let's say you got your surface, and should probably walk over to Morey Field and look at the pitching machine there. So, gosh, that would be really fun actually if we had campus open. And you guys, I don't think that I'm allowed to have students in the classroom yet. That would be kind of cool actually. Yeah, don't think it'll happen this summer, unfortunately. To actually play around like baseball machines or stuff like that. So baseball right now is kind of in here, right? There's a baseball. So this is the before. The after is going to look like this. I think I'm drawing like that one. If someone watched Star Wars or The Empire Strikes Back, one of those like robot machines that walked in the snow. I think it's called the AT-AT or something. I can't remember. But it looks like I'm drawing that. Anyway, so now the ball leaves. It's being fired. Fired out of the pitching machine. So we kind of assume everything's at rest. I'll tell you that, but you know that's what's happening right before the ball leaves. Everything's at rest. And then what happens is that this is the velocity of the baseball. And the velocity of the pitch, as you can imagine, if it fires a ball out, the pitcher is just kind of probably move back a little bit. If you kind of think about like, and a little bit, shouldn't really talk about guns, especially at a school, but if you were to shoot a gun or rifle, if anyone ever has, kind of scary actually, if you've never have, but you know, if you're holding a gun or rifle, once you fire it, the rifle moves back a little bit, right? I mean, that's kind of what you would expect. So that's what's happening here. So initially everything's at rest. So we're going to do our initial velocity, P0 equals PF. So basically you have the mass of the pitching machine initial plus the mass of the baseball, times the velocity of the pitching machine initial plus the mass of the baseball initial times the velocity of the pitching machine, baseball initial. So you're looking at the pitching machine, momentum initial, baseball, initial momentum. And then of course you have the mass of the pitching machine final times the velocity of the pitching machine final plus the mass of the baseball final times the velocity of the baseball final. The masses are not going to change. I'm just being very nitpicky here, but we're not going to expect that to change. So for the mass of the pitching machine is 5, and there's no velocity initially, and the mass of the baseball is 0.15, and there's no velocity of that initially. So really we expect that to be 0, the initial momentum. So final momentum has to be 0 also, but the velocities will be different to counteract it. So I'm being very consistent here. Even though you could have just set the momentum of the pitching machine equal to the momentum of the baseball and adjust for the sign of the opposite signs of the velocity, let's be consistent. Let's use the same formulas here. I want to be universal with you guys. So that's 5. We don't know this, so leave it like that. That's 0.15, and of course it moves at 35 meters per second. So 5 times VPF plus, let's use a calculator. So you have 5.25. Move that over to the other side, so it becomes negative 5.25. Divide by 5, you should get negative 1.05. So we expect the machine to kind of move back a little bit, opposite direction of the baseball. That's what you would expect, right? So that is what we have. And 35 meters per second, in case you are curious. Let's see here. I'm gonna go to Google on my phone. 35 meters per second of miles per hour. So about 78 miles per hour, which is kind of slow for like major league standards. Probably high school, it's about right. College is kind of okay. But if you've ever been to a batting cage, 70 is really, really fast. So if you're not comfortable hitting the baseball, that definitely is really, really fast still. So it's even more impressive when those guys hit a 95 or 100 mile per hour baseball and hit it out of the park. It's really, really impressive when it happens. So if we look at the answer key really quickly, make sure we did everything fine. Yep. It should be negative, by the way. So I'm not sure why they made it positive. Yeah, they have a mistake here. So I did all this correctly. They put 2 negatives, so that's a mistake. That's a typo. That should be negative 1.05. It should not be positive. They had this correct, 5 times V plus 5.25, whatever that is, when we calculate that part, but that should be negative on the other side. So, but everything else they did correctly. So, yeah, it should be negative, by the way. So the sign will matter because velocity is a vector. Okay, hopefully we're comfortable with all this. No questions? Okay. I'm surprised I haven't made a mistake yet. So, but thanks for those who correct me. You always have to be careful. This is, human error is very rampant with stuff. So let me turn off the recording.